right, everyone. So while we get settled down, maybe I'll do a quick couple of announcements. Um, we do have the quiz on Friday, and as I mentioned, it's on Castigliano's theorems for beam frame problems and the force method. So please do take a look at the sample quiz that I've posted on Blackboard. And if you come up with questions or you need to confirm answers with each other, feel free to post on the Blackboard forum. Anybody took a look at that quiz yet? No? Okay. Um, and next week is, of course, spring break. So there won't be a homework due next week, but there will be a homework due the following week on Friday, the usual time. But before I decide that, um, uh, I was thinking whether I should make the due date for the homeworks Saturday 5 p.m. rather than Friday 5 p.m. Would that help? How many of you feel Saturday would be better, but part two would still be due on Monday at 5 p.m. because I want to keep every homework week to week? Okay, so most of you seem to think that Saturday 5 p.m. would be better. I'll make sure I do that. The other thing that I want to mention is that homework 7 that I will post will involve some of the MATLAB codes that I've been talking about. So if you're not really familiar with MATLAB, take a look at the introductory lecture, couple of lectures that I did on basic programming things. And I'll also post links to quick introductions for programming with MATLAB if you're not familiar with it. So so that by the end of the spring break, you should be able to at least figure out what the program that I've given you is doing, how it is doing that, and what possible changes you might need to make to it to solve the homework problems. Okay? Any particular questions before we jump back into solving indeterminate trusses with the computer methods? Okay, so what I'll do is I'll very quickly remind you how we got to this point. So we had been talking about this method of joints for determinate trusses. And I told you that essentially the algorithm for this method of joints is to sequentially draw the free body diagrams for all the joints, write out the corresponding equilibrium equations, and convert this set of equilibrium equations to a system of linear equations that looks like this. Now, the trick I told you was, how do you create this system of equations, this matrix in particular? How do you create this matrix automatically? How do you get the computer to create this matrix for you? And I told you that a very specific pattern is what we make use of to try to create this matrix. Anybody remember what that pattern was? How did we create this matrix for the method of joints? Okay, this is something that I'll wait on for you to respond. Say it again, Drew. Are you? Oh, April is pointing at somebody, so let's ask April.
Is it that every element is connected to two nodes and affects those nodes only?
That's correct. So if you look at the unknowns that are there in my system of equations, these unknowns are the 7 member forces for this particular truss. This particular truss has 7 member forces and 3 unknown reactions. So if I look at those 7 unknown forces and the 3 unknown reactions, they correspond to the number of columns in this matrix. And for each column, I'm talking about a particular member A. And as you said, one member is connected to exactly 2 nodes, which means that it will contribute to the equilibrium equations for those 2 nodes, both in the X and the Y direction. Sometimes one of those components is zero because the member may be oriented exactly in the x direction or in the y direction, which is okay. But it will contribute to exactly four places, two nodes, two equations for each node. So it will contribute to exactly four places. So the way to generate this matrix automatically, we said, was loop through each element in the truss. So go from A, B, C all the way to 7, run the loop 7 times, and go to the correct location in the matrix and put in the correct value of that coefficient. The value of that coefficient was simply obtained by geometry, by this geometric table. We said element A, or maybe let me pick something else. Element E, for example, here. Element E is right here, connected to nodes 2 and 5. Connected to nodes 2 and 5. The X component of this element E that applies a force at node 2 is 3 divided by 5. So that's why I have a 3 over 5 here. The Y component of element 2 applies a force of negative 4 over 5 at node 2. So that's how I get these two values, and the values for node 5 would be just opposite of those two numbers. So if I go back to this matrix, look at column E, I have 3 over 5, 4 over 5. That's the contribution to node 2. I have minus 3 over 5 and plus 4 over 5. That's the contribution to node 5. So in this way, if I loop over all the elements of my truss, I can calculate this first 7 columns of this matrix very easily. And the rest of the 3 numbers here are simply obtained by looping over the unknown support conditions, the unknown boundary conditions, which is basically saying that x displacement is fixed, y displacement is fixed, and x displacement is fixed. So that allows me to create this matrix automatically in a computer program. And the right hand side vector is just a vector of loads 10 and minus 10 applied at the correct degrees of freedom. And once this matrix system has been constructed, MATLAB can solve it in no time for you. And keep in mind that this system of equations is basically what I'll refer to later as well for indeterminate structures. That when we solve a system of equations A, unknown internal forces and reactions N, for applied loads F, I'm writing that as A times N equal to minus F. So this is something that I'll use again and again for the indeterminate structures later on. So keep in mind how this works. And I went through the code also quite a bit to show you, I think, which particular lines of code are doing what. So let's go here. I told you that the main program for that determinate trusses is statically determinate truss 2d.m. If you run that program, it gets input from the user, calculates different things, and this one call to the most important subroutine, which is called solve truss 2d. That one call solves that truss for the internal element forces and the support reactions. And after that point, you just plot the results. I also told you about how to calculate these coefficients for the truss element and add the support columns in this matrix A. And this one line right here, solve matrix system equations, this is where we are solving that A n is equal to minus F. In this one line, we are solving that system of equations. And once we do that, element forces and support reactions are just certain elements of that solution vector. So that's how we solved a statically determinate truss. And last time we had begun, I'll skip this computation of automatic computation of displacements. I think it's reasonably straightforward. Essentially, if you want to calculate the displacement at a node in the x direction or in the y direction, apply a unit load at that degree of freedom, solve the structure, and use the virtual work method, virtual forces time real displacement. And that allows you to calculate the displacement at each and every node in the truss. So it's a loop. You're solving the determinate truss again and again. to find displacements at each one of those nodes. Once you have those displacements, you can easily draw the deflected shape, right? Now, this is something that you wouldn't be able to do, or it would take a long time to do by hand. So that's why we are looking at how to do this systematically in a computer program. All right, so first we need to make sure we understand how we had solved the determinate trusses. And based on that, we are going to use all of that machinery to solve indeterminate trusses using the force method. So I told you last time that for indeterminate structures, normally you get a system of compatibility equations. Maybe I'll repeat that a little bit. So if you remember long back when we were talking about that force method, we said that essentially the idea is remove a redundant force, find out the actual displacement, and then find out the displacement due to a unit redundant load, and use compatibility equation to solve for the unknown redundant force. That's the force method in a nutshell. We're going to use that force method to calculate redundant forces for our indeterminate truss. And I also pointed out that if you have multiple redundant forces, for example, if you have two redundant forces, By and Cy, what you end up getting is a 2 cross 2 system of equations, right? In this, you need to solve an underlying determinate system at least 1, 2, 3, 4, 5 times. Okay, so even if you have a degree of indeterminacy 2, you end up solving a system of end up solving a determinate structure 5 times. Not something you want to do by hand, even for a small degree of indeterminacy. So if the degree of indeterminacy is higher, for example, for this truss, there are 6 panels, degree of indeterminacy is 6. So what you will get is a 6 cross 6 system of equations, compatibility equations to solve for all the 6 redundant unknowns. So for example, if you chose all the diagonal elements in one of the diagonal elements in all of these panels as redundant forces, these would be your 6 redundant diagonal elements. And to solve for that, you would have to calculate how many? 6 plus 5, 11 plus 4, 15 plus 3, 18 plus 2, 20 plus 1, 21. 21 flexibility coefficients and 6 actual displacements. So 21 plus 6, 27 times you would have to solve the underlying determinate truss. Absolutely nothing you want to do by hand, right? So, but the good thing is we know how to solve a determinate truss now. We have a nice program in MATLAB which doesn't really care how many times you want to solve a determinate truss. Just put it into a loop 27 times and it will run all the analyses for you in practically no time. And what we do need to do is to figure out a way, figure out an automatic way to let that computer program run the analysis 27 times for this truss for us, and that way we can make use of the program that we've already developed to solve indeterminate trusses. Okay, so here's how that will work. I'll start with a simpler, smaller problem. Let's take a look at this truss. This is exactly the same truss that I had before, except there is in the truss before, I did not have that support at 5. Now that was a determinate truss. As soon as I put this support at 5, it becomes an indeterminate truss with a degree of redundancy of how much? 2. I have an unknown fx and an unknown 5x and 5y force applied here that causes redundancy. So I will break it up into 2 parts, an originally determinate truss, which I'll call actual truss, and a redundant truss, which is those 2 redundant forces applied at the correct locations. So if I can figure out what is the correct 5x force and what is the correct 5y reaction force that needs to be applied to node 5 so that the original truss does not have any displacement here, then these 2 trusses put together would be equal to my given indeterminate truss. That's the logic. This is the same logic that we used with the force method also. How do we get the computer, or how do we get MATLAB to do it for us? Let's see how to do that. So First part is being able to solve the actual determinate truss. How can I do that? Just call the function that I had previously. You remember an minus f? That was the system of equations that we were solving. This one right here. Exactly this system of equations. You give me the correct loading, and this matrix has already been computed. I can simply make one call to that subroutine, and this will solve it for me. What does it give me? It gives me NA. NA are the internal member forces and the three reactions here for the actual applied loads in the absence of any reactions at 5. So that's the first step. That was what we did with the force method, solve the actual system. Now, what the next step is, we need to solve the redundant system. Since there are two redundant forces here, I would have to solve the redundant system twice. Once for a redundant force at 5x, and a second time for a redundant force at 5y. So that's what this equation represents. So for example, if I apply a unit load at 5x, I would have 0, 0, 0, 0, and 1 at the 5x degree of freedom. And for that force vector, I can solve for all my internal forces using that same subroutine that we had developed. I'm just changing the right-hand side vector. This matrix A does not change. And what that allows me to calculate is NR1, which is basically all the internal forces in all the members and the reactions for 5x. Then I go to the second redundant force, 5y, apply a unit load here, solve for all my internal forces and reactions. Once I have these two, then I have the solution to the actual problem and the two redundant problems. Okay, and in general, you might have many more redundant forces. So that's why I've written it as a sort of a sequence of redundant problems. I have one actual problem and a sequence of redundant problems. Here's a question. For this particular problem, how many redundant problems would I have? 6. I would have 6 equations here. For each one of those redundant forces, I'd be trying to find out what are the internal forces here and the reactions, right? So, right. So if now hopefully that makes sense. So for this particular truss, I'm showing you an example how that works. Look at this first vector. There are exactly 10 entries here. Why 10? There are 10 entries here. Why 10 entries? 2 for each node. There are 5 nodes. There are 5 nodes. There are 2 degrees of freedom per each node. And if you look at the last or the second but last entry, that's a 1 here. So node number 5 in the x direction has a unit load in this first column. So if I solve that first column for that matrix A that I showed you earlier, I would get this as the solution. Let me ask you this. Does this solution make sense? What is this solution telling me? If I apply a unit load at 5x, let's go back here. If I apply a unit load at 5x, what would be the solution to this problem? You see, if I only apply a unit load 5x here, 1 unit here, that will cause tension 1 unit here, that same tension 1 unit here, and a 3x of -1 in the opposite direction, correct? All the other members would be zero force members, right? If I apply a 5x unit load here, only members F and G, those would be corresponding to columns 6 and 7, or rows 6 and 7 in my unknown forces, and 3x would be corresponding to the last element in my solution. So if I check that, I have 1, 2, 3, 4, 5, 6, and 7 elements have a unit load, and 1x, 1y are 0, and 3x is -1. So the solution vector for a unit load applied at 5x gives me the correct solution. Of course, it should. since I'm solving it against an A matrix that we had constructed for the determinate truss. Similarly, if I apply a 5y unit load, I get the solution vector, which is internal forces in the members and the reactions at all the three locations. So solving for this matrix, which I'm calling NR, these are the internal member forces for the redundant systems. So I'm calling this NR. Solving that system is pretty much straightforward using that solve 2D truss code that I had showed you. Once we have that, uh, we have the actual response and we have the redundant response. What do we need to do then? In the force method, what did you do? You found, uh, in the force method, if you found this, and if you found FBB, what did you do after that point? We just use compatibility to find the unknown redundant force By, right? So if I know delta B, which is the deflection of the actual system, if I know flexibility, which is the displacement at B due to a unit load at B, and in our system, the flexibility is actually a big, uh, uh, we still need to calculate those displacements actually. But we have found the internal forces. We have found the internal forces due to the actual loads and due to the redundant loads. So we need to actually find the displacement at 5x and 5y due to the actual loads, and we need to find the displacements at those 2 points due to the redundant loads. So that's the next step. Um, so to calculate those displacements and then be able to use the compatibility equations, we have these two compatibility equations in this case. There are two redundants, 5x and 5y. We want the displacement at those two redundants to be 0. So we are saying that displacement due to the actual load at 5x plus displacement due to the redundant loads at 5x should be 0. And similarly, displacement at 5x due to actual load, 5y due to actual loads, and 5y due to redundant loads is 0. These two compatibility equations are an exact analog of this type of a compatibility equation where we had two redundant unknowns. So I had two compatibility equations. I expressed them in terms of a matrix, and then I was able to solve for the redundant unknowns. That's what I'm trying to do with MATLAB in an automatic fashion now. Okay, so let's see how do we do that. To calculate the actual displacements, here at 5x and 5y, how would can anybody tell me how can I do that? I know the internal forces due to the actual loads. I know the internal forces due to the redundant loads. How do I calculate displacement 5x, for example? Ivan? Right. So we can use the virtual work method. That's what you're saying, really. That we know that if I want to find the horizontal displacement at 5, I apply a P prime at 5. Or in this case, I'll just apply a unit load at 5. So I know the virtual forces. I will take those virtual forces, multiply them with real displacements, which I can obtain by NL over AE for the actual loads. And so virtual forces times real displacements gives me 5x. And that's what this statement out here is saying. Virtual forces times real displacements. I know both of these things. L over AE is well known from the input file. So I can calculate actual displacements at 5x and at 5y using this one line. And similarly, to calculate the flexibilities, I will be using the redundant forces square, n square L over AE, right? That's what you did for your truss problem for indeterminate trusses. To calculate flexibilities, we used n square L over AE. This is exactly uh, that computation, but I've written it in form of a matrix so that I can compute it in MATLAB in one command. I don't really need to do that um, repeatedly. So I'll show you that also in a bit. And finally, I'm making use of this matrix FM in here. What is FM? FM is just so that I can take the actual loads and multiply it with the correct value of L over AE. So for example, for element A, L is 3. So that's 3. B is 4. That's 4. C is 5. D is 4. E is 5. And F and G are 3 and 3. So this matrix helps me to take my actual loads N and multiply it with the correct amount of L over AE. So that's why I'm calling it a global unassembled flexibility matrix. So if I take F, this matrix, times the N matrix that or the N vector, which is the vector of internal forces for actual loads, which we obtained on the previous page, right here, NA. If I multiply those two matrices, I get my real displacements, take those, multiply them with the virtual forces, and I get my displacements, my actual displacements. Similarly for the redundant displacements, and once I have that, um, I get a system of equations of compatibility, which all of these numbers, so there are these 1, 2, 3 numbers, and because it's symmetric, so I don't really need to compute all 4, 3, and plus 2, 5 numbers. These were all computed by these two lines. Once I have these two lines computed, I can solve this system of equations for my unknown redundant forces 5x and 5y. And so once I have those unknown redundant forces computed, I can go back and add these two systems correctly and be able to solve that will give me the solution to the original indeterminate problem. So now conceptually, this is a little more involved than a statically determinate truss. But keep in mind, all we are doing is the force method, solving a determinate system plus solving a redundant system. And there are some tricks in here of how to actually calculate those displacements. But again, this is not something that I expect you to be able to code it up by yourself. I will give you the code for this, but you should be able to understand what's going on in that code. And I will go through the code that right now, giving you sort of big highlights of which parts of the code are doing what. But maybe before I do that, I can show you at least how it works. So the main program for this indeterminate truss is called Truss Flexibility Method 2D.m, which I'll post to Blackboard. So all you need to do at this point is I'll create a breakpoint here, which is one line to solve the indeterminate truss. So before I solve that truss, I'll create a breakpoint, run it. It tells me, it asks me for an input file. So I'll choose my first input file here, open. And this is the truss that it's showing me from the input file. This is the truss that I was just showing you also, right? A couple of key things to note about this truss. At node 1, there is a roller, but it's fixed on both X and Y. So when you look at your input files, this is just a way to visualize the input file. So if you go back to this truss, there is a pin here, fixed displacement in the X, fixed displacement in the Y. So this picture says that X displacement is fixed and Y displacement is fixed. And this picture at 3 says it's a vertical roller. Okay, it's free to move in the Y direction, but not free to move in the X direction. This is exactly what we have in our given problem also. Okay, and similarly for node 5, I have the same type of pin connection. X displacement and Y displacement both are fixed. There are 10 and minus 10 loads at 2 and 4. So this is the original given problem to me. All I've done is just plot the input file. Now we'll go to that subroutine. In this one call, I'll just say step 1. And in that one call, it has solved for all the element forces of the indeterminate truss. Okay, support reactions for all of the for the indeterminate truss, and then this one line plot truss 2D again plots the results. There are my results. So you can actually again zoom in and see that there is some X reaction, Y reaction here. This is a member in tension 6.3033, and all the internal forces in each one of those members are marked. This one is a zero force member. It tells me all the reactions at all those points. So essentially, with this one call right here, solve indeterminate truss 2D, which is doing all of the things that I had just told you about. This one call solves element forces and support reactions. This plots it. And after that, all I'm doing is to try to calculate the displacements using the virtual work method. I want to find out under these internal forces and reactions, what are the displacements of node 2, node 3, node 4, node 5 doesn't have any displacement. So what are the displacements at these three nodes? How do I do that? Miles? Virtual work. That's exactly what we did for the determinate trusses. The virtual work method does not care whether it's a determinate truss or an indeterminate truss. If I want to find the displacement at 2, apply a unit load at 2 and apply unit load at 2 in the y direction. Same thing, do that for all the nodes in this problem. And essentially, that's exactly what's going on. For all the nodes, go to each node, apply a unit load in the x direction, unit load in the y direction, calculate virtual element forces using the indeterminate truss subroutine, and just using the virtual work method, then you can compute the displacements and plot. So I'll let it run through, and I have the solution for the deformed truss. You can verify. Clearly, there is no displacement at node 1. There is vertical displacement at node 3. There is zero displacement at node 5, right? As it should. This so so even for a complicated, well, this is not too complicated, but even for a degree of redundancy of 2, a method like the force method, which you would have to calculate 5 different displacements just to solve the internal forces, and then to solve for actual displacements at the nodes, you would have to repeat all that process to find the displacements at each one of those nodes. So there would be lots and lots of calculations here, but if you find a way to automate that process, MATLAB will do it for you in practically no time. Maybe I'll run some of the other examples also, and I'll briefly go over that indeterminate truss 2D subroutine. So let's run this again with a second input file. This is probably one of the examples in your book. So once again, for a load applied here, calculate all the internal forces and calculate the displacements at each one of the nodes. Everything here uses the virtual work method. Yet another example. This is the example from your homework problem, right? So if you can solve this example, and you can actually solve the symmetric half of this problem also. I think that's input file number 10, but I don't remember. Let's see. Yep. So if you solve that symmetric half of the problem or that full problem, you should get the same response, and which you do. I think maybe in the solutions you have those two pictures. This is the subroutine that we use to generate those two pictures. Excuse me. So let me now talk a little bit about what those input files look like. They look like very similar to what we had for the determinate truss. So I'm getting into this MATLAB program. So maybe this is a better place to do that. Um, for this truss, there are 5 nodes, just X and Y locations. So the input file just contains nodes information, element information, which is basically 7 elements here, telling which nodes, which 2 nodes are connected. So you can easily verify that those are the correct element connectivities. We have boundary conditions or support conditions, just as before. In the previous determinate example, you remember there were only 3 rows. 1 is fixed in the x direction, 1 is fixed in the y direction, 3 is fixed in the x direction. Now node 5 is also fixed in the x and y directions. So I have 2 extra boundary conditions in this problem. I have loads, exactly the same loads at node 2 and node 4 in x and the y directions, 10 and minus 10. And unlike the determinate truss, I have something extra here in the input file. I have something that says define the redundant members or redundant reactions. So typically, for an indeterminate truss, you would have to pick what things you want to make redundant. In this particular case, I am saying that this reactions at 5x and 5y, these are the redundant things. But that's not necessary. I could just as well pick something else. I could pick, for example, 3x and 5y maybe, or I could figure out a different combination of members and reactions. As long as the underlying system, when I remove those redundant members, is determinate, it's good. Right? It doesn't matter what redundant system you choose, as long as the underlying redundant system you choose is determinate, that solution is fine. So in this particular case, redundant elements is empty. I'm saying there are no redundant elements in my case. Redundant boundary conditions, I'm saying 4 and 5, which is basically the 4th row here. That's the reaction 5x. And 5th row here, that's reaction 5y. I'm saying those 2 reactions are redundants for this particular problem. Okay, so that's the only extra thing that you would have to specify in your input file to for this particular truss example. Once you do that, you can call the main program, which is truss flexibility method.m. You can see that the initial portions of this file are exactly similar to that statically determinate problem. There is a tolerance for 0 forces. This line here, feval line, that is just getting get input from user. This is just plot to check the input. This was the main call that I told you where we had placed the breakpoint in the MATLAB code. This one call solves the indeterminate truss. Solve the indeterminate truss in this one call. Once you do that, plot solution. After you plot the solution, calculate element lengths, that is LM for the virtual work method. And the rest of this is to solve for displacement. So as you can see, what's really happening in this case is that I've put a for loop, all of that thing up until this end, between for and end. This entire for loop is apply p prime, calculate the indeterminate truss for the p prime in the x and the p prime in the y directions. So this is basically calculating the virtual internal forces for the x direction and the y direction. Then this dot product is taking the virtual element forces nm and multiplying it with the real displacements dm, which are nothing but actual forces times lm divided by ae. So that's again doing the virtual work method to calculate displacements at each one of the nodes of the indeterminate truss. Once you have those displacements, just plot them. So that's out here, plot displacements. Question? No? So let's take a look at how this all-important subroutine that I've written here, solve indeterminate truss 2D, how does this work? And I won't get into too many details here, but what I'll try to do is to try to correlate certain sections of this code with the logic that I gave you on the previous in the handout. So what's happening in this case? The input to this code is node information, elements, element EA information, boundary condition of supports, what are the loads, what are the redundant elements, what are the redundant boundary conditions, and AMAT. There are 7 inputs to this subroutine. What does it output? It outputs element forces and support reactions and also AMAT. So this AMAT is both there both in the input and the output, and is used as an optional argument because really I don't really want to calculate this A matrix again and again. If I calculate it once, it remains constant for that problem. So the very first time I call this program, I call it without AMAT, and I use that AMAT as an output. And every time I call it after that point, I'm going to provide AMAT so that this subroutine does not waste time calculating that AMAT matrix. And the way that works is right here. There is this command called nargin in. What this is saying is if number of arguments to the input call is equal to 7, that is 1, 2, 3, 4, 5, 6, 7. If there are only 7 input arguments, then I know that AMAT has not been provided, which means that I need to create an A matrix. So that creation of A matrix goes exactly like we had done for the determinate truss. You see that for loop, that for and this end, you are calculating that mx for node I and my for node I. You are assigning that in the correct location for the A and for node I essentially, and then for node J. Those 3 lines or those 6 lines are constructing my A matrix with 4 entries for each row like we had discussed. So if I this is for each of those 7 elements, create that A matrix. That's what's going on here. This is something we had talked about for the determinate trusses also. Once we have done that, we need to add columns. This is add columns to A due to reaction forces. And here there are 1x, 1y, 3x, 5x, and 5y. There are 5 reactions here. So the A matrix in this case actually would not be symmetric, would not even be square. There are more number of unknowns as less number of equations. So that should be expected. And we'll see that in a little bit. Finally, create the right-hand side vector of loads. So this is loads. And that is just creating A times N is equal to minus F. So that F is what we have created here. And at this point is the indeterminate. So up until this point, it was very similar to what we did for the determinate trusses. Beyond this point is where we are doing, where we are trying to use the force method to solve the indeterminate truss problem. So let's see how that works. Indeterminate truss using force method. So first I need to define a primary determinate truss, and in this case we do that by deleting the redundant members from the A matrix or deleting the redundant boundary conditions for the A matrix. So you remember we said that 5x and 5y are the redundant boundary conditions in this case. So we delete those particular columns from our A matrix. That's this right here. Once we have the correct redundant members, this RD and ND are exactly the same variables that I used in my handout here. So this is RD, and let's see, ND is just the number of redundant unknowns. And maybe what I'll do is actually run through this and show you how it works rather than go through it one thing at a time. So once again, what I'll do is I'll put a breakpoint at this line for the call for the solve indeterminate truss. Choose that input file. Input is OK, and therefore I want to go into that. So now look at indeterminate truss 2D. I have the correct node information, correct element information, EA, and all of those things are in here. I'll go to that point where the go to this line where the indeterminate truss solution starts. So go to that point, and now you should be able to see that primary element numbers, there are 7 elements. So those are the primary elements of the truss. Primary boundary conditions, there are only 1, 2, and 3. The redundant boundary conditions are 4 and 5, as we had seen before. I'll also show you another thing here. The A matrix is 10 cross 12. Can anybody tell me why is it 10 cross 12? Say that again? No. There's 5 nodes, right? There are 5 nodes, Ivan. Right, so if you remember for the statically determinate structure, it was 10 cross 10. There were 5 nodes and 5 times 2, 10 equations. So it was 10 cross 10. But this is an indeterminate problem. I have only 10 equations, but 12 unknowns really. So the number of columns is 12. There are 2 extra columns in this A matrix. And that's why when we do the primary redundants, so A mat columns, and there's a primary A matrix, which is the correct 10 cross 10 for the determinate system. And the rest of it is basically going through these 2 computations and finally being able to calculate the redundant forces. So I'll stop at this point. I'll try to, I think what it will need for you to do is to do exactly what I'm doing here in class. Put a breakpoint at some location in your code and try to follow along exactly one step at a time how those things are being computed, and try to make sure that you follow that those computations are actually exactly what is given in the handout. Okay, so make sure you go through the code, go through this handout, Try to make sure you understand how the code is working, and then I think you'll be able to use it without any trouble. Okay? All right, so we'll stop here, and I'll see you back on Friday for the quiz.